You know, for the better part of a century, we've been sketching out a map of reality. We've charted everything from the tiniest particles to the biggest structures in the universe. And honestly, this map has been incredibly successful. But lately, we've started finding glitches, little cracks in the map that might not just be pointing to new places, but to a whole new world we never even knew existed.
So let's just dive right in with the big one. What if our fundamental understanding of the universe is, well, wrong? And look, this isn't just some late-night philosophical question. This is a question being forced on us by cold, hard data from our most powerful experiments. What do you do when the universe starts sending back error messages that don't match the instruction manual we wrote for it?
To really get why these cracks are so important, we first have to appreciate the map itself. Our whole picture of reality today is basically built on two incredible, rock-solid theories. And together, they explain pretty much everything we see, from the phone in your hand to the most distant galaxy.
Okay, so pillar number one is this beauty, the standard model of particle physics. Just think of this as the ultimate recipe for the cosmos. It tells you all the fundamental ingredients, the matter, the forces, the whole shebang. And for decades, every single test we've thrown at it, it has passed with flying colors. Well, almost every test.
The other pillar is all about the big picture. It's called the Lambda CDM model, which is just a fancy name for our best, most detailed version of the Big Bang Theory. This is the grand story of our universe's 13.8 billion year journey. For a long, long time, these two theories together gave us this beautiful, neat, and tidy map of reality.
But here's the thing about science, right? It absolutely loves a good mystery. Because when you build these unbelievably precise instruments, you start to see things in the fine print. Little places where the map doesn't quite line up with the real world. And that's where the first signs of trouble always begin.
And that brings us to the most important word for this explainer, anomaly. Now, it might sound like a bad thing, like something's broken, but in science, it's the exact opposite. An anomaly isn't a failure, it's a clue. It's a giant flashing arrow pointing and yelling, "Hey, look over here. Something new and exciting is happening." So, let's make this real. Meet the muon. It's kind of like the electron's heavier cousin, about 200 times more massive. And it has this really cool property. Like a tiny spinning top, when you put it inside a powerful magnetic field, it doesn't just spin, it wobbles. It has this very specific wobble to it.
Okay, and this is where things get wild. The standard model, our cosmic recipe book, makes an insanely precise prediction about how much that muon should wobble. But when physicists actually measured it over and over again, it wobbled just a little bit faster than predicted. A tiny difference, sure, but a difference that just refused to go away.
Now, you might be thinking, okay, a tiny difference, maybe it's just a statistical fluke. Well, physicists have a way to measure that. The gold standard for saying this is a real discovery is something called 5 sigma. The muon wobble anomaly isn't just at that standard, it's beyond it. 5.1 sigma. It has officially crossed the finish line into this is real territory. Let me put that another way. The odds of this result just being a random error are about 1 in 3.5 million. So no, this isn't just a smudge on our map, this is a genuine crack. It's as if some invisible, unknown particle that's not in our instruction manual is out there giving the muon an extra little nudge.
All right, so a wobbling particle is one thing. But what if a crack appeared in the entire story of the universe itself? What if our most powerful time machine sent back a picture from the past of something that just shouldn't exist?
And that time machine, of course, is the James Webb Space Telescope. What an incredible piece of engineering. Its whole purpose, its main mission, was to look so far away that it's actually looking back in time to see the faint light from the very first galaxies switching on at the dawn of the universe.
And you know what? It worked. Oh boy, did it work. It saw those first galaxies. But there was a huge surprise. As one scientist, Lior Shamir, put it, what JWST was seeing wasn't an infant universe. The galaxies it found already looked big, mature. They looked way too old for their age. And this really lays out the paradox.
Based on how far away they are, we know these galaxies existed when the cosmos was just a toddler, maybe 500 million years old. But when we look at their shape and brightness, they look like fully formed adult galaxies that are 10 billion years old. It's like finding a fully grown oak tree where a tiny acorn should be. It just doesn't make sense. So naturally, the headlines went a little wild. You saw it everywhere. Did the James Webb Telescope just break the Big Bang? I mean, it's a massive question. Is our entire origin story wrong?
Well, not so fast. This is science in action. Before you throw out a century of physics, you check everything else first. Scientists are exploring all sorts of possibilities. Maybe star formation was just way more efficient back then. Or maybe supermassive black holes got an earlier start, supercharging galaxy growth. Now, some of the most extreme findings have been revised, but the core tension is still there. The early universe grew up way faster than we thought.
So let's recap. We have a tiny particle that wobbles too much, and we have giant galaxies that grew up too fast. Now, you might think these are totally separate issues, but to a physicist, these aren't problems. They're clues. They're breadcrumbs leading us somewhere new.
And I know it sounds crazy. What could a wobbling muon possibly have to do with ancient galaxies? But this is the holy grail of what scientists call new physics. The dream is to find one single, elegant new idea, a new particle maybe, that doesn't just solve one problem, it solves a bunch of them at once. What if these two very different cracks are actually connected?
And this is a little glimpse of what that search actually looks like. Now, don't worry about reading every single box. What this web shows is physicists literally mapping out all the different known anomalies. They're trying to connect the dots to see if one new undiscovered particle could be the single cause for multiple of these glitches. This whole field has a great name, Beyond the Standard Model Physics. And it's basically a systematic hunt. Step 1, find the anomalies where data and theory don't agree. Check, we've got those. Step 2, dream up a new particle or force that could explain it. And step 3, this is the crucial one. Check if your new idea also happens to solve any of the other big mysteries without breaking all the stuff we already know works.
Think of it like a cosmic detective case with a lineup of usual suspects. These are all hypothetical new particles with some pretty wild names, like leptoquarks or a Z-prime boson. Honestly, the names aren't important. What is important is that each one of these is a potential candidate for that single missing piece that could be causing all these cracks in our map.
So where does all this leave us? We've got this beautiful, powerful map of reality, but it's a map with confirmed glitches, confirmed cracks. And this isn't the end of the story. It's the beginning of the next unwritten chapter. And that really is the most important thing to take away from all this. Headlines might scream about a crisis in cosmology, but for the scientists doing the work, this is the most exciting place to be. A complete, finished map is a dead end. These anomalies, these glitches, they're the X's on the treasure map, marking the spot where the next great revolution in science is buried.
Which leaves us with one final, mind-bending question to chew on. Are these glitches just small fixes, like we're just correcting a few street names on our existing map? Or are they showing us that our map covers just one tiny country on a vast, undiscovered new continent? Could these cracks be the first hint of something as profound as a multiverse, where other universes with totally different rules exist? That's the frontier, and these cracks are our very first glimpse of what might lie beyond.
Welcome to the Deep Dive. Today, we're jumping into some really fascinating puzzles in cosmology. We're looking at these surprising observations, the ones that are making us rethink, or at least refine, our standard picture of the universe. We've got some great sources lined up, stuff from the James Webb Space Telescope, analysis of the cosmic microwave background, all pointing towards potentially new physics. So our mission today is to explore these cosmic glitches, these anomalies, and see how they might be whispering secrets about how the universe really works.
Let's kick off with the James Webb Space Telescope JWST. I mean, what an incredible instrument.
Oh, absolutely. Its infrared capabilities are just phenomenal. It's like a time machine, letting us peer back into the very, very early universe.
And that's where things get really interesting, right? Because JWST started seeing these, these galaxies that looked surprisingly mature and bright, too.
Exactly. At really high redshifts. We're talking redshifts like Zez around 15, which means we're seeing them when the universe was maybe only 500 million years old. But they looked. How old? like galaxies that are normally 10 billion years old, some even with spiral arms.
Yeah, it was quite the shock. The analogy used was like finding, teenagers hanging out in a kindergarten classroom. Didn't quite fit the expected timeline of galaxy formation in the standard lambda CDM model.
Okay, but I heard there was some nuance there. Some of those initial measurements were maybe a bit off.
That's right, yes. Some of the very first really extreme photometric redshift estimates, those are based just on brightness and different filters, were later revised downwards when they get spectroscopic confirmation. So maybe not quite as anomalous as first thought for some.
Oh, okay.
And this is important, other confirmed observations, like Jade's DSC-14 Dessert, are still genuinely puzzling. This one has a confirmed redshift of 14.32. That puts it at just 290 million years after the Big Bang.
Wow, that early.
And while it's small, maybe 1,600 light years across, tiny compared to the Milky Way's 100,000.
Yeah.
It's incredibly bright and just packed with stars. A real pocket powerhouse.
So even with revisions, we're still seeing unexpectedly vigorous activity very early on. How are cosmologists trying to square this with lambda CDM?
Well, there are definitely efforts within the standard framework. People are looking at things like maybe star formation, which is way more efficient back then. Or perhaps supermassive black holes grew incredibly quickly, triggering these massive bursts of star formation.
Right.
It could also just be that our current computer simulations of galaxy formation, they might be missing some key physics for that early stage. They're incredibly complex simulations after all.
Makes sense. But I also noticed, even in the material we looked at, some mentions of older, maybe more, fringe ideas making a comeback.
Yes. That's definitely bubbling up in some discussions. It's interesting. Because these anomalies are pushing boundaries, some researchers are revisiting Fritz Zwicky's tired light hypothesis from nearly a century ago.
Tired light, remind me.
The basic idea is that maybe, just maybe, redshift isn't only due to the universe expanding and stretching light waves. Zwicky suggested that light itself might lose energy somehow as it travels over billions of light years, like it gets tired.
And if that's true...
Well, if light loses energy intrinsically, then very distant objects would look redder and therefore seem further away or older than they actually are based just on expansion. It could offer a different way to explain why these early galaxies seem so mature. It's definitely an alternative perspective, not mainstream, but being discussed.
Okay, fascinating. Let's switch gears then. If JWST is looking at the universe's toddlers, the cosmic microwave background, the CMB, is like its baby picture, right? The afterglow of the Big Bang.
Exactly, the earliest light we can see, and lambda CDM has been spectacularly successful at predicting its overall properties, statistically speaking.
But not perfectly. There are these anomalies here too, especially on the largest scales in the sky.
That's right. Despite the overall success, some persistent oddities remain. One of the big ones is called power suppression.
Power suppression.
Yeah, it basically means there's less temperature fluctuation, less correlation on the very largest angular scales, looking at patches of sky bigger than about 60 degrees across than the standard model predicts. The blank satellite measured this very precisely. The value they found, this S12 statistic, was like way lower than predicted. The chance of seeing that low a value in standard lambda CDM is less than 1%. It's statistically very unlikely, almost too smooth on the biggest scales.
Less than 1%. Okay, that's significant. And wasn't there something else, kind of directionality?
Yes, the dipolar modulation. It's like there's a preferred direction superimposed on the CMB fluctuations. It's subtle, seen in correlations between different scales.
Yeah.
But it shows up with over 3 sigma significance. And there are other, maybe weaker hints too, things like a slight preference for odd patterns or parity, and a tension in how much the CMB light seems to be gravitationally lensed by intervening matter.
So multiple little statistically weird things in the baby picture. Is there any theory that tries to connect these dots?
Well, this is where things like loop quantum cosmology, or LQC, become quite intriguing. LQC is a theoretical framework trying to understand the very beginning, potentially resolving the Big Bang singularity.
How does it help with the CMD anomalies?
Instead of a singularity, LQC suggests the universe might have bounced from a previous contracting phase. This pre-inflationary bounce phase could leave specific imprints on the largest scales. What's really interesting is that LQC seems to change the expected probability of observing these anomalies.
Changes the odds.
Yeah. So remember the less than 1% chance for the power suppression in standard cosmology. LQC calculations suggest the probability of seeing what we see could be much higher, maybe around 16% or so.
So it makes our universe seem less freaky, less statistically unusual.
Exactly. It potentially makes these features less anomalous and more like something we might actually expect if LQC is on the right track. It even suggests a possible common origin for both the power suppression and that dipolar modulation.
Right, linking them together.
Potentially, yes. It provides a framework where these aren't just separate, unrelated oddities.
So, wrapping this up then, it sounds like these anomalies, both from the early galaxies seen by JWST and in the CMB, they aren't necessarily breaking cosmology.
No, not breaking it, but definitely bending it, maybe stretching it.
Right, they're pushing us, forcing us to refine the standard lambda CDM model, or maybe, just maybe, consider entirely new physics. It really shows how much more there is to learn.
Absolutely. The more precisely we measure the universe, the more subtle and fascinating the questions become.
Which leaves us with a pretty profound thought, doesn't it? If these are cosmic whispers we're just starting to decode, what other truths, maybe even about what came before the Big Bang, are still out there waiting to be heard?